We can
Okay.
wait. We can wait five
Yeah.
5 minutes. I think.
Yeah. Okay. And let's see if others join. Otherwise, we'll start. Okay.
Yeah.
Okay. So I guess you can start. Okay. It's, let me just share my screen. You can see my screen, right?
Yes.
Okay. So this is week 10, and so the goal of this week is to practice, right? Is to practice whatever we have learned so far on plotting, right? And let's see. So first of all, we will get a data set, okay, which is kind of rich in terms of plotting, and then we will go for like whether how many plots we can do on the data set. Okay. So there is this weathers data set, right? From there we can actually do some really good plots. So you can also download it. Yeah. So this data set, okay, weathers. So it's, so let us see first which columns are there and what they basically means. Okay, so it's actually let's say there is
Yeah.
weather measurement.
Can you share the link in
Oh, yeah.
chat?
Yes, we have the link in the chat. This one. Okay, so what it captures is basically temperature, like humidity, wind speed, wind bearing, these kind of things. Okay, wind directions, like visibility, okay, and cloud cover. Okay, and also it also kind of gives you how much it is, like partially cloudy, mostly cloudy, or others. There are, like, we will see which values are there, and also whether it is rainy, whether snow is falling, something like that. Okay, so let's say we want to um, develop a model to predict whether there will be rain today or not. Okay, so based on the data, we want to predict whether there will be like, there will be rain in the area or there will be no rain. Okay, so let's just download the data first. You can download it from here as well. resources here. Okay, so the data set is weather history.csv. Okay, we just
Yeah, so you are downloading from the download link.
yeah, here. So it will give you an archive. Okay, and then after you extract it, it will kind of give you a 16 MB file, which is the data set. We click on this one, download. Okay, let me just source kind of being activate Jupyter. Sorry. Okay, so we now have wiki 10. Okay, so we
You
want
were
to,
able to download. You were able to
oh
download when you clicked on downloads.
yeah. So I'm actually logged into Kaggle. Okay, so maybe you have to log into Kaggle, then you can download. Okay.
Yeah, I logged in. I
Mhm.
logged in, but still it's not downloading.
Okay, so let me just put it to the, wait, let me just put the uh, file in here. Wait, log sheet. I can put it in the drive, right? There, from there you can download it.
Okay. Now I think now it started download. Yes.
Okay, so I will also put it in the drive. Okay, so if anyone can, you want to download from there, you can download it. Okay, later on. Fine. Okay, so
Yeah.
just for the others who
It's a
joined a little,
zipped file. And
yeah, it's a zip file.
it's
Yeah,
a
it's a
zipped
zip
file,
file.
and inside it there's CSV file. Yeah.
Yeah, download it. Yeah, just unzip it. There will be a CSV file, weather history.csv, something like that. Okay. So see, now for the others to have, just to give you the context, what we are doing, we are trying to do some analysis on a data set. Okay, plot some plot some of the like kind of, let's say, observations from the data set, and then just do a modeling on top of it. Okay, using some, let's say, Python libraries, that how we can, and our objective is, so we are handling this weather data set. Okay, so our objective is to predict whether there will be rain or not. Okay, so we will do all the analysis to understand whether there will be raining today or not. Okay, and so by doing this, you are basically practicing all these things, that data analytics part and the plotting part. Okay, and one new thing we will learn today is how to do basic modeling on Python, that how I can train a classifier. So earlier in the like in the sim, this one, right, in the sentiment analysis part, there was a classifier, but I didn't explain that code, right, because it was a TensorFlow code. So today we'll like do a little bit easier library, that scikit-learn library. Okay, which is be easy, which will be basically like very easy to learn and apply to any of the problems. Okay, let's see now. See, now to read that, so what are the libraries we required? So to read the data, we need pandas, right? So pandas to read a data frame. So pandas as pd, and then we also need numpy. So currently we don't need numpy, let's not import it right now. So let's also import matplotlib, matplotlib dot pyplot as plt. Okay, and what other thing we require? We don't require any other libraries for now. Okay, let's just import these two libraries only. Now let's read the data first. pd dot read csv, and I have kept the file in resources, weather history, this one. Now if I read it, see this is the data. Okay, and it's basically day wise as far as I can see. Is it day wise? So 2006 4, so it's data from 2006 to 2016, so 10 years of data. It's a very big data. Okay, now so what is the frequency here? Let's see. One. To see how many samples we have per day, what we can do, see, this is the formatted date column, right? So I can see the formatted date column. Okay, now I only want to see how many like entries. So it's actually hour wise, as far as I can see, it's actually hour wise. So for one day I have 24 entries, 0 to 23. Let's see if I just uh, want to see only top 23 entries or 24 entries, it will be like this. So head 24 gives you top 24 entries. Okay, and see, these are all from the same date, and if I go for 25 entry, that will be for the next date, I guess. Oh, so the date are not sorted, but anyway, it's a different date, right?
So
So you
how
have to
are
sort.
we importing the file? How are we importing the file into this?
Yeah, this one, this pd.read csv. We are using this library called pandas. Okay, and it actually read the
No,
whole
so
csv
when
file.
we downloaded the file, it was in our downloads. So then we
Uh-huh.
have to change the location of the file.
Yeah, so what I did, I actually kept it inside this resources folder here. See? So now I am,
In
what I
your
am doing,
system.
yeah. So what I am doing currently is my this is notebook I am opening here, and there is this resources folder. Here I have the CSV. So what I am giving as a path is dot is for current directory, dot slash resources, then the path, the file name. Okay. So this is how I am reading the file. So basically nothing. It's like I am giving like a relative part to that file, and I know that the file is like situated in this directory, so I can just do dot slash resources slash weather history.csv. Okay, and it basically gives me what? It basically gives me this data frame. This is known as a data frame. Okay, so all the columns are there and the rows represent the data. Okay, you get it, right?
So this dot means like we don't have to give the full path C drive, like the
Yeah,
full path.
no. So you can always keep the full path. Okay, so let's say the file is not in your like. So why I am giving relative path? Because my notebook is here. You see, my notebook file is here, week 10. So I am giving this directory. Go to the resources folder here, and then you have this file for the CSV, right? But let's say your file is under downloads, so I will give you the absolute path. So basically I am giving relative path because it's like it makes sense to give relative path for my case. But if your file is in, let's say, C drive downloads, then you can give a absolute path as well, not a problem. Okay, so I can, anyway, I can give an absolute path here as well. Let's see what will be an absolute path for this. Let's see, resources, yeah, this is the absolute for my case. User where something, I just copy paste it here. Now if I read it, it will read the same file. Okay, but anyway, why I am not doing this? Because it will only run on my machine, right? Because this path is true for only for my machine only. But if I give this dot slash resources, that anybody who is organizing the files as me, as here, right, resources, they can run the code without any modification. Okay.
Okay.
Okay, so
So
it's better to use absolute path whenever possible. So sorry, relative path.
so just the folder name and a dot.
Yeah, yeah. Dot means, so this dot means current directory. Okay, so whichever current directory I am, and then slash, go from current directory to this subdirectory, and there you find a file here, like which is named whether history.csv. That's it. Okay, and let's say if you want to let's say read this file, right, somewhere outside this folder. So dot means actually this folder, this pmrf underscore nptl folder. Okay, and then dot slash means go to the subdirectory resources. Dot slash resources means, and there you will find this file, whether history.csv. And let's see, if I want to read a file which is outside this directory, outside the parent directory where the file is located, I will give a dot dot. So let's say I want to read a file here, and let's say pictures, okay, which is let's say, which is actually outside the parent folder, right, outside the folder where the code executes. So what I can do, I can just do dot dot slash pictures, let's say pictures, p capital. See, all the other directories which are outside this folder comes as suggestions, right? So this dot means current directory, dot dot means before the current directory. Okay, so for my case, I
Okay.
will just keep dot. Let's read it. So let's see what are the columns. So this is how you can see the columns, how many columns are there. So formatted date is one column. Summary is so we'll see what summary means. Let's see, let's just print top 5 entries. Okay, which will be easy to analyze. Let's say, so this is date, that's clear to us. This is date, time, and which is formatted in terms of hour. So in each hour I have a data, and the data is for 10 years from 2006 to 2016. Okay, now summary is basically what it is, basically partially cloudy, mostly cloudy, these type of things. Okay, for that whole hour. And then this is actually whether it is rainy or whether it is sunny or snowy, this kind of data. Okay, and so to see from where this data is coming from, you can also see here that there's like usually what this data set also mention where the data is collected from. Okay, uh, let's see, metadata, collaborator, author, license, with the data, wait, discussing. Okay, no. So for this data set, they didn't mention any documentation, but okay, there are some data set is my GitHub profile as well. Okay, which I worked earlier, and these data sets actually collected by us. So you can find some good data sets here as well to explore. One is this one. Second is this. No, not this one. This is the code base. This is the data set. Okay, so this is one example of a good data set we published before, and this is another data set. Okay, so see, this is how people usually document data sets as well. Okay, so they give all the necessary information that are required to analyze the data. For our case, kaggle, that like for this data set, people didn't bother to document it, but anyway, so these are some good examples of like documented data sets. So for example, this data set have like bus trails. So what we usually did is, let's say there was one volunteer who board a bus and then just go from one location to another. So this is one route, okay, where bus usually travels. So and he also marks all the stops. So why the bus stopped. So whenever a bus stopped, he marks that okay, there is a turn here. That's why the bus, let's say, speed down, or let's say stopped in a signal or somewhere. So the volunteer marked that event. Okay, so now the data set contains trajectories So all the, let's say, inertial data, so gyroscope, accelerometer, all those data, as well as the tagging where the bus stopped. Okay, so yeah, so here you see these are the modalities as far as GPS, speed, altitude, accelerometer, gyroscope, Wi-Fi, light and sound. Okay, so from light you can know, okay, it is, so anyway the data is also time stamped. Okay, so from the light also you can see whether it is night or day. Anyway, from the time stamp it is obvious, but from the sound you can say where the bus is more crowded. Okay, or which part of the whole trajectory, whole, let's say, route people usually board more, or let's say where the bus is mostly empty. From the sound profile of the data you can tell those things, right? So these are some good, like, well documented data set. You can find like the code, the related code, as well as the paper here. Let me share you these things. These are some good, so the paper you can also read actually, so then you know how we had analyzed the data for this one also. So this is another data set which you see, by reading the initial abstract you can understand what is this data set. Okay, so what it is basically indoor air data, okay, from 30 indoor sites, which is basically households, canteens, these kind of stuff. Okay, household, canteens, studio apartments, or let's say labs, classrooms, this type of indoors. Okay, so we have collected data for 30 indoor sites, and what we did, we kind of do this type of deployment. You see, this type of deployment, that okay, there is an indoor location, we have placed these sensors which measures a lot of pollutants actually. So we placed these type of sensors in multiple locations of the house, and the occupants, what they have to do is they have to annotate their activities. Okay, so when they are going out, when they are eating, when they are cooking, say, which are annotated here, when they wake up as well. So whenever people are sleeping, that also generates pollutants. Okay, so whenever, let's say, 2 or 3 people are sleeping in a same room, they generate pollutant in that room. Okay, so to know that context, people has to also annotate their activities. So we have this data set over 6 months. Okay, and it's around like 90 million samples. Okay, currently it's all like a little bit bigger now, so we have to update the data set anyway. So it's around 90 million samples we have for 30 households. So this is a lot of data, right? And the data columns are like this. So timestamp is there obviously. Without timestamp, these data doesn't mean anything. These are temporal data, right? Now temperature, humidity, PM 2.5. So PM is particulate matter, which is very small dust particles. Okay, so there are, so 1, 2.5, 10 means these are different diameter particles. Okay, let's say 1 means it is 1 micron, 2.5 means 2.5 micron. And why this diameter matters is because our breathing, right, our we cannot filter particles less than 2.5 meter or less than equal to 2.5 micron diameter. So these what they like, so 10 meter, so 10 micron particles, that they are basically filtered by our lungs. Okay, so we didn't usually have any health impact for 10 pm 10. Okay, but pm 2.5 and pm 1, these are very easily like enter into our system, enter into our body by our breathing rate and all those things, right? So these are very harmful for us. So these sensors, these sensors are also there in this sensor. Okay. So they measure all the concentration and all. Also these pollutants. So ethyl alcohol, VOC, carbon monoxide, all those things. Okay. Okay. So this is one data set, good data set that you can see, and the associated paper is there. So there are 2 associated papers actually. So you can read them if you want to. One is this one. Another one, you can go to my scholar and see actually. Another one is this, yeah, this one. Okay, see you the link. wait, I have the archive link, see from there, see from here. Okay, view PDF. Anyway, if you are interested, then you can see the analysis from that paper. Okay, what we have analyzed on the data. But anyway, these are some, like, the primarily how data sets are organized. But for kaggle, I don't think, because it's a kind of unrestricted platform, and they, like, necessarily they don't come with papers and all, right? These are open source data, so that's why they are usually not documented, or sometimes you will get a good documentation based on your luck. Okay, for us, we don't know where the data set is coming from, but I guess it's something from California side or somewhere. Okay, let's see that we will get a documentation for the data set somewhere else. Yeah, GitHub pages here. Okay, so yeah, this one, this data set is that one. Okay. No, it's actually a bigger data set. So it is from dataset project. Okay, by, let's see where this guy is coming from. If you listen, you know Delaware. I guess he's from US. Okay, so this data set, yeah. So he's from US. So this data set is from US, and it's actually from different like all the like measurement units they have deployed over the country. This data set is actually getting data from all of the sites. Let's see whether they have some visualization or not. No, their visualization doesn't work anyway, but this data set would be very much like interesting to explore. Okay, let's just do our analysis on the small data sets first. Okay, and then we will see whether we can download this data set. I guess it will be very big. It will be, I guess, 3-4 GB or something. Okay, but so similar data set is there, this weather.csv, which is from multiple weather stations deployed. So 122 weather stations deployed throughout USA. Okay. Okay. Okay, so first thing, so we have to just formulate the questions part. So what we want to know about the data set. Okay, so our goal is to predict whether it will be rainy or not rainy. Okay, so let's see how much percentage of the data set is consisting of rainy hours and how much percentage is not consisting of raining hours. Okay, so this column, right? So let's just mark our objective somewhere. So goal is to predict uh, rainy or not. Okay, so this is our goal, and what we want to know first. So Q1, how much data is of rainy hours and how much is not of rainy hour. Okay, this is our first question. How we can get that? So this is the column. You just take that column out of the data frame. So this is how you take the column out of the data frame. Okay, you just give It's basically dictionary type call. Okay, and then you do value counts. We have already showed this function earlier in the earlier week, right? Value counts. So it will give you a dictionary of all the unique values, counted unique values. So there is only two type of labels. One is rain and is snow. So I guess it is somewhere from top of USA or somewhere. Okay, so when there is only two weathers, rainy and snowy. Okay, so anyway, anyway, we will predict whether it will be raining or snowing. No? And the data. So we have these two numbers, but these two numbers doesn't give us directly sense of how much the data is from rainy and how much the data is for snow, right? So what we can do for, let's say, so if I just give you these numbers, right, it doesn't give me directly the quantity, right, how much percentage is from rainy and how much percentage is for snowy. So to represent this, the best plot is to do it at pie plot. Okay, so I can just do a pie plot which represents the percentage as well as the count. Okay, so to dict, which will give me a dictionary, right? Now for them, from the dictionary we can plot a pie chart. Okay, so plt dot pie and x means the data, exact data, right? And then we have to also give labels. Labels means the exact labels. Let's say A and B. This will give me a pie chart. Now for these two, how I can do it? Just say data rainy. Just save it to a variable data rainy dot values. So values will give me, so dictionary dot values give me the values, right, the actual data, and keys give me the keys for each respective values, keys. Yeah, so this is how much is raining, this is how much is snowy. And now to also have the percentages, right, what we can do, we can just do this keyword autopact, right? Autopact is equal to, and if I do shift tab again, there will be some examples for autopact as well. Okay, so if you don't remember it, how autopact works, you can see it from here, or let's say search it anywhere. Wait, autopact, yeah, this one, right? So okay, so I didn't see any direct answer. So anyway, so I will search autopact. Yes. Matplotlib pie autopact. Yeah, it goes to the go to the first link, and this is how you use autopact. So %.2f means like print a floating point value from the second, like, to the second decimal place. That's it. Okay, so %.2f. Yeah, we need second decimal place. Yeah, so 88 point, and I can have a percent after that. Wait. Autopact 2f, and then if I want to have a percentage after that, how they have implemented it. Okay, so I can also do this. Okay, either I can do this as well, it should work. What they're saying, incomplete format. Okay, whether this would work. No, so anyway, so if I want to add a percentage after that, what I can do, is have a different function altogether, make auto fact. Okay, and instead of passing this string, I can pass the function, and this make auto fact function send another function which has this type of format that keep the percentage and the value as well. Let's see. So what they're saying, okay, make auto fact values, and values are this. Right. Okay. Now see, I have the percentage as well as the exact number. So to make them in the bottom, to have just them in the bottom, we just do a slash in here instead of space. It gives me this full representation, right? Okay. Now I can also do, so sometimes this explode explode also helps. If I give explode is equal to 0.1, what they say, okay, it has to be same length. So two data points, so 0.1 comma 0, it will give me this kind of a cutout type representation. Okay, so rainy is 88.8% and the snowy percentage is 11.17%. Okay, so this gives me better representation of, or anyone from, let's say if you want to put the data on a PPT, right? So instead of giving the exact values, this type of plot would look good. Okay, and people will directly understand by looking into the plot. They don't have to like understand whether the data is, or they don't have to, basically their cognitive load get reduced, so they don't have to think too much to understand the data. Okay, so first question is this, we solved it. Okay, now second question. Okay, so what is our data set? Now we know that 88% is rainy and other percent is snowy. Okay, now we will see from the, whenever there is raining, how much is the humidity, and whenever there is let's say snowing, how much is the humidity, whether there is a difference among humidity, temperature, all those factors or not. Okay, so by to understand that, there can be two plots, one is bar chart and another one is this box plot or distribution plot. Okay, so anyway both of them are, but sometimes this box plot is like more acceptable in many scenarios. Okay, for example, let's say, so the bar chart only gives you the central tendency, right? Mean or median, these kind of measures. Whereas this box plot gives you mean as a like central tendency as well as variance, right? How much the data is varying. So in most of the papers or most of the reportings, wherever I have seen this type of scenario, let's say you want to represent a group of data, right? They usually represent it in a box plot, not a bar chart. Okay, why? Because bar chart only gives you the central tendency, it doesn't give you the let's say the variance. Okay, so we'll use, let's say, a box plot for this. Okay, and we'll show that, okay, from rainy and snowy, if I compare humidity and temperature, they are different, very different. That's why it's raining or snowing. Okay, okay. So how we can plot it? See, now dot temperature. First of all, we have to, like, let's say, first of all we have to split the data from rainy to snowy. Okay, and then we have to understand temperature and humidity separately. So one plot for temperature, one plot for humidity. Okay, so how you can do that? Dot. Now to slice the data where there is raining, I can do this. I already know the column name is this. Okay, I can do a boolean operator is equal to rain. So whenever there is rain, it will give me true. See, all the initial things are true. Meanwhile, there are some positions where there will be snow. Okay, so if I do a mean of this dot mean, okay, it will give me how much percent. See, 88.35%. 88.35. Okay, anyway, so this means this much percentage is rain, which is similar here. Okay, now all this is boolean data, right? Now if I just pass that boolean data to data frame again, it will give me a slice of all the data which is having this column as rainy. Okay, so this is how you filter data from a data frame. That okay, I want to get all the data points where this column is rainy, okay, or rain. So I can first get a boolean. Okay, this bracket is not necessary. This bracket is not necessary. Okay, I can get a boolean array of that and then just pass the array in a data frame. It will also give me the subset where all the values are rain. Okay, now this is rain data, right? Df rain. Similarly, we can also just do a not operation here, not rain, which gives me all the data for snow, right? Or you can write snow here is equal to snow if you want, is equal to snow. Okay, now snow data we also have, so let's see whether we have snow data or not. Yeah, so for all these things we have snow. Okay, now these two data frames are there, fine. Now for rain, I want to see rain and snow. I want to compare the temperature, right? So the dot, so I can get the temperature column by this tempera temperature. Sorry, I have the wrong spelling there, I guess. Temperature, oh no, that is this the bracket C as well. Anyway, here temperature, right? Now to represent this data, and this is for only rain, right? So to represent this data, what I can do a box plot. So how I can do a box plot? Plt dot box, and you guys know already box plots, right? Your box plot, these are known as box plots. These are known as box plots. Okay, what they mean? You see, there is this cool representation. Yeah, so see, this middle line is known as median or 50 percentile. Okay, Q1 is for 25 percentile, Q3, so this is quartile 1, quartile 2, and these are kind of the, let's say the first quartile and the maximum quartile, and this is actually IQR, interquartile range. Okay, so these two IQR, and this is the whole range, maximum and minimum value. This is for 25 percentile, median is for 50th percentile, Q3 is for 75 percentile, and the rest of 25 percentile happens to be in the Q3 and maximum value. Okay, and anything which is outside this range is considered as outliers. Okay, and outliers, how we consider them as outliers? This is the equation. So if it is from Q1 minus 1.5 times IQR, then it is an outlier, or if it is Q3 plus 1.5 times IQR. Okay, or sometimes we also can choose to be, let's say I want all the data which is 2 standard deviations away from the mean to be outliers. So this type of logic. So in this case they consider that, okay, from Q1 if it is 1.5 times below than the IQR, this interquartile range, then it's an outlier. Okay, and same for the maximum range as well. So this is a box plot, and the data represents mean means, or median means it's a central tendency. Okay, median, in median times the temperature is this, let's say 20 degrees. Okay, we will see. Let's plot it. Box plot and pass this data. I have this box plot. So you see the median median temperature is from 10 to 15 degrees, somewhere around 14 degree, I guess, somewhere around 14 degree, and these are some outliers. So there are some situations when there is rain but the temperature is around 40 degree, okay, which is very unlikely. Let's say it's somewhere near summer or somewhere, okay. 40 degree, if it is raining, it's obviously summer, okay. And there is some data which is around 0 degree. So there are some instances where there is raining in winter as well, okay. So that's why this box plot actually represents our data very nicely instead of a bar chart. So if I am doing a bar chart, then I will lose all these observations and only get this median representation, right? A median or mean, let's say anything, any central tendency I choose, let's say median or mean, let's say median. So I will only get this 15-degree bar and I will lose these observations that okay, there is some instances where even if the temperature is 40 degree, it was raining. So it was some instance of, let's say, summer or some other instances, okay. So these observations we miss in terms of bar charts. Now if I want to plot a similar diagram for snow, so that whenever there is snowing, so obviously the median temperature will be lower as per our hypothesis, right? As per any hypothesis per se. So I can just pass them in a list like this and just replace this snow, and now I have two bar charts. You see, two bar charts and two. See, these are our outliers, okay. These are our outliers because they happen very infrequently, but they happens, okay. So I can remove them by just passing a parameter as false, show flyers or something, yeah, this one. So this is whether you want to show the outliers or not, I can just pass them as false, it will not show the outliers now, okay. So see, our hypothesis that okay, whenever there is raining the temperature would be high and whenever there is snowing the temperature would be low is correct, okay. Now let's see whether humidity is similar or not, okay. Similarly, I can rain temperature, snow temperature, humidity column is what? Humidity, only humidity. Humidity, humidity. Now see, there is one mistake here, right? What is the mistake? Is that I have plotted both of them in the same figure. So if I want to plot them in different figure, I should not run them together, okay. Just run this first, okay, and then this one, yeah, this looks good, right? Let's just do a plt.show here just so that these prints are not coming. Plt.show, okay. Now see the difference. See, this is for and we can actually name them, just name them for our understanding first. Plt dot. So one good practice is to, whenever you are doing a plot, you should label the plot correctly, okay. Otherwise it's very hard for people to understand, okay, what the x-axis mean, what the y-axis mean, these things, okay. And this is very important. So only plotting a graph is not sufficient, you have to also label the the data, right? Okay, x-axis is this, y-axis is this, or any other data. Let's say you want to also color the graphs, right? Based on the color there can be different meanings, okay. I'll show you later on anyway. Plt dot x label, right? So the column is x label, not x label, x ticks. So these things I want to label, right? X ticks 1 and 2. So x ticks, and see, I can pass ticks and labels, right? So these two things I have to pass, okay. I already know that the ticks are at 1 and 2, from here, and the labels I want for them is to be rain and snow. See, now it's rain and snow. And for y ticks, I don't need anything. It's from, let's say, minus 10 degree to 40 degree. So instead what I need a y label, right? I need a white label that represents, okay, this is the temperature column. So this is a temperature, temperature, and it's in degree Celsius. Okay. Yeah. So now see, okay, rain temperature is, median temperature is around 15 degree, and for snow median temperature is below 0 degree, which is obvious, right? Now similarly for snow I can do these things, just copy them, paste them. Just here I have to change it to humidity, and humidity is actually in so for this case it's around in fractions, but like usually it represents a percentage value. Okay, from 0 to 100%, what is the humidity? Okay, so to have it in percentages, what I can do, I can just multiply the data with 100, right? Just multiply both the data points with 100, and it gives me in humidity, and it's in percentages now. These choices you are like supposed to make whenever you are representing some data. Okay, sir. Okay, usually people understand humidity in terms of percentages, so we should represent the data in terms of percentages, even if the data set gives me a data from 0 to 1. Okay, so these type of scalings you are supposed to make assumptions on your own. Okay, now let's, and see, this is very hard to compare, right? So what I can do, I can have two plots together in terms of side by side. So how I can do that? So anyway, we have the plots, you can anyway see them by zooming out, right? See, what is the observation from here? So observation is whenever it's raining, the temperature is high with respect to snowing. Okay, and whenever it is snowing, the humidity tends to be high. So this is actually very crucial observation, that see, to be snowing, the temperature should be very low and humidity should be very high, then only snow happens. Okay, like in the other case, when let's say temperature is low as well as the, let's say, humidity is low, in that case only raining will happen, right? That's why, see, there is some instances where the temperature is very low, okay, but only rain happens. See, here the median temperature and this temperature is very close, right? So if snow only depends on temperature, then this should be actually not here, right? It should be far away from 0, far away, let's say something positive. Okay, so but what we can see here, that okay, the rain, so the snow not only depends on temperature, it also depends on humidity. So the humidity should be very high. Okay, otherwise snow part, like the snowflakes would not come together, and it's like snowing will not happen. Okay, okay, anyway, uh, let's just do another thing, that let's see how to do subplots. Okay, so I can have them side by side in two different plots. How I can do that? Figure comma axis is equal to plt dot subplots, this one subplots, and I need, see, this number of rows, number of columns, all those things. So I need one row, two columns, right? So one row is default, so I need two columns only, columns equal to 2. So now if I run it, you see there are two columns, right? And these are like jumped up, so this is jumbled up, so we should fix the plots and all. So now to have this axis, so this x and y axis, let's see what axis means for this. Okay, so axis is basically two axes, so this is one axis and this is another axis, and we have named this as label, y label is something, temperature C. Okay, so these two axes we have in terms of an array. So axis 0 gives me the left axis, axis 1 gives me the right axis. Okay, so I have to just change this from PLT to axis 0 to plot in this axis, to axis 1 to plot in the other axis. Okay, so PLT axis 0 box plot gives me, let's run it. So it gives me these things, but this label is still here and this label is also still here, right? So this is wrong. So how I can shift them? Axis 0. Now for to set ticks of an axis, the code is set x ticks. Okay. Similarly for y labels, and this is like throughout the matplotlib library is same. If you are plotting in an axis, it is set axis, set tick, set labels, these things, and if you are plotting directly, it's only x ticks, x plots, or plot. Okay, these things. Axis 0 dot set. Okay, yeah, now see these two things shifted to the axis 0 or the left side axis. Similarly, I can just copy the below code, right, and wait 1 minute, we just okay. So to switch to axis 1, I can just do, yeah, like this, copy paste it, set, set. Now see, I can directly visualize them side by side. Okay, now one problem is there, one problem you can directly see is this humidity label is coming on top of the axis, right? So you can shift it to some degree. But to do that, we can use the figure size parameter over here. Figure size, zoom it, fig size, okay. And so fig size, let's see what it means actually. Yeah, so this means the number of the width of the figure, and this is the like the breadth of the figure, okay, or the height of the figure. So let's keep it as 8,3 for now. Okay, anyway, that's still some bit overlap, so we can increase this to 9. Yeah, now see, they are perfectly side by side. Okay, so now the observations is pretty obvious, right? So let's say I want to explain that, okay, when, let's say I want to explain in my PPT that when rain happens or when snow happens, I can directly annotate it and say, okay, see, when rain happens, what is the observation? That temperature is usually high and the humidity is less than the snow humidity, right? But for snow, when to snow to happen, the temperatures must be low and the humidity must be high. This is the observation. Okay, so this is our analysis. So analysis 1, analysis 2. Analysis 2 is rain happens when temperature is high and humidity is relatively low. AVELY, relatively low. Similarly, snow happens when temperature is very low and humidity is relatively high. Okay, this is a good observation we have. Now let's go for another question. Okay, so what is our data set? So currently what things we know that the most of the data is for rain, right? And this is obvious because rain can happen any time in the year, but snow can only happen in winter, right? Which is, let's say, a fraction of the year. Okay, now similar observation what we can get, let's see the data set. Temperature, humidity, apparent temperature means it's something like feels like. Okay, so temperature is the absolute value, apparent temperature is feels like. So it's basically whether how much it usually felt in indoors and other environments. Okay, this is outdoor temperature and this is kind of an indoor temperature you have. Okay, anyway, these are correlated and we can plot it actually. So anyway, it is already known that indoor temperature and outdoor temperature will be correlated, but anyway, to know it, if like kind of without any confusion, you can just plot them side by side with a scatter plot. Okay, so we have this data here. So we want to know, the question is whether yeah, it is whether indoor and and outdoor temperature is correlated or not. These are usually correlated. Okay, so the second column is this, right? We can just cut them, do a scatter plot, plt dot scatter, and just pass both of them. For x, let's say, pass the outdoor temperature, for y pass the indoor temperature. And why we pass them as x and y? Because this outdoor temperature is the cause, right? So we should put the cause in x and the effect in y. Okay, usually to scatter plots and all, not for these plots. So these are discrete plots, right? These are rain and snow we want to compare, so they don't basically these are discrete things. Okay, but anyway, for line plots, for scatter plot, all these things, when the variables are kind of dependent and independent relationship we have, in that case the independent variable should be placed at x. Okay, and the dependent variable should be placed as well. See, the indoor temperature is dependent on outdoor temperature, so that's why we placed outdoor temperature in y. Okay, and the logic is y is equal to f of x. That's why we placed the dependent variable in y. Okay, and this is the scatter, and we can just do a alpha. Alpha is equal to 0.443. So you have plot like this. This is so it's mostly linear, right? So you can place a regression line over here. Wait, so to place a regression line, you can do seaborn as SNS. Okay, seaborn, and in case of scatter we just do rig plot. SNS dot rig plot, and it doesn't get an alpha parameter. Yeah, so it plots a regression line, and you can actually color it differently, I guess. Wait, see this line keyword arguments. This line keyword arguments, you can pass a dictionary where color is, let's say, red. Okay, Yeah. So this is the regression line. So what it gives me is that, okay, if temperature is 10 degree, my apparent indoor temperature should also be, it should be around 0 degree. So why it is so? Wait, let me see. So outdoor temperature is 10 degree. That, no, so it's around 10 degree anyway. So see, it's correlated, right? 10 degree 10. So it will be easier for me to understand if I turn on the grids. So this is how you can turn on the grid. So all the x and y axis lines will be there. Yeah. See, for 10 degree, the indoor temperature is also 10 degree. Right? For 20 degree, the indoor temperature is also 20 degree. 30 degree, it's also 30 degree. Sometimes it's lower or higher. Let's say someone is using a AC. In that case, it can be lower, right? So let's say for 30 degree, okay, there are some instances where it is lower from the regression line, right? So in that case, let's say someone is using some AC to control it, to let's say control it 26 degree or 27 degree or something. Okay, but anyway, the point was that the outdoor and indoor temperature is correlated. Okay, they usually vary similarly, somewhat differently due to AC and all those things, but mostly same. Okay. Okay. Uh, Now what else we can do? Wind speed, okay, and wind degree, from which degree it is coming and what is the speed. Okay. Visibility is whether we can, visibility means how far we can see. Okay, let's say it's a foggy weather or something like that, and this here we can use, like, do a very cool plot actually. So for raining for snowing, we can see how much visibility is affected. Okay. Cloud cover, cloud should be, I guess, cloud cover. Okay. Pressure in millibars and daily summary. So partly cloudy throughout the day, partly cloudy throughout the day, partly cloudy throughout the day. Okay, these things. Okay, anyway, this is not required. So summary gives us a short form of this. So anyway, so this column is actually a much detailed version of this summary column. Okay. So anyway, so what we can do, we can see two things. So our whole analysis is to understand what is the difference between rain and snow, right? So whether the features or the other data, except for rain and snow, whether the other data points are different in terms of rain and in terms of snow, and which columns are different basically. Okay, so this temperature and humidity we already established. Okay, these are showing different characteristics, and we have that written here, right? Now what is remaining? The apparent temperature, okay, it is correlated with temperature, fine, no problem. Wind speed, wind degree. So wind degree, I don't think it has any particular meaning in this case, because wind degree is dependent on the, let's say, on the continent, right? For India, I guess, for, let's say, rainy season, right, wind degree is from north. Okay. So these type of things, I don't think it will affect too much, but wind speed, obviously it impacts it, right? For example, whenever it is raining and whenever it is snowing, the wind speed should be different. Okay. So these two things, wind speed, visibility. Cloud cover, I don't know whether it means anything useful. Let's see. Cloud cover or cloud cover. Okay, so from here, you see, from here also we can understand, okay, most of the data is 0. So this data doesn't make any contribution to the prediction. So you can just throw this out. Cloud cover, I think it is cloud cover or something, they have mislabeled it. Anyway, but it contains 0. Okay. So you just throw this column out. This kilometer visibility will see. Wind direction, I don't think it will have any impact. And this wind speed should obviously have an impact. Okay. So wind speed, it's wind speed, this one. Okay, and we want to know what? We want to know whether uh, we have difference in terms of snow and rain, right? So you can use the same plot over here. Let me just copy this thing. Wait. Copy this thing, put the data to be wind speed for 1, says wind speed, labels are rain and snow, fine, ticks are fine, the y label should be wind speed, and the other data point that I want to plot is this visibility, right? Millibar, this pressure also should have some impact on it. We'll see. The pressure is also dependent, so how much air pressure you have also impacts it. Wait, let's see. Wind speed, visibility. I want to plot the second thing as visibility, and we don't have to multiply it to 100, okay, because it is not in from 0 to 1, it's from kilometer. Okay, now if I run it, now let's see which thing impacts is the most. Wind speed. So what we saw that, okay, it's mostly same, but for snow it is the median wind speed is lower, but for rain the median wind speed is higher. That's obvious, right? For snowfall it is mostly steady wind speed. Okay, I like if no, okay, not in the case of a snowstorm, but anyway. So there are high instances as well. Let's say 25 kilometer per hour wind speeds. When let's say there is very uh, like rough snowstorm or something like that. Okay, anyway, but the median means most of the time the temperature, sorry, the wind speed is lower in terms of a snowfall. Okay, with respect to raining, let's say anything. Okay, visibility, see, snow reduce visibility quite a lot, right? So in case of snow the visibility is quite low, but as for rain the visibility is quite high. Okay, if you ignore these cases, let's say when there is raining cats and dogs or something like that, a very high degree of rain. Okay, so there are separations. The visibility is very much separable in terms of rain and snow, but for wind speed the separation is little bit kind of marginal, right? So it's not that much separable. Okay, see these boxes are very much overlapped. Okay, so okay, so which columns we understand so far? Visibility, pressure. So one column is remaining, pressure. So you want to see, let's say which plot we can do for pressure. This is the pressure, right? So we can do a distribution plot. Who is calling? Let me just take this call. Okay. Oh, okay. So you can see my screen, right? Hello.
Hello.
Fine. Yeah, I can. You can see my screen, right? Hello.
Yes.
Okay. Okay. So see this pressure, right? I can do a distribution plot in this case. So because it's only one value, I can, instead of doing this, another representation of the same data would be to do a distribution plot. So how I can do a distribution plot? I can get this data which is only for rainy, right? Which all the pressure values, this is only for rainy, and then just do SNS seaborn dot histogram, or KDE plot. I can also do KDE plot, which will give me a distribution. Okay, so see, these are some cases where the data is missing actually. So zero millibar pressure cannot happen, right? So it gives me some data which is for 0 millibar, which is obviously noisy. Okay, so what we can do, we have to remove this data, right? So how these things are removed, uh, we will compute the mean. So this is how you impute data. Okay, we compute the mean, compute the standard deviation of the data, and we see whether my data is below than 3 standard deviation. So minus 3 times standard deviation. So if my data is below this value, and this gives me a scalar. Okay, if my data point, if my value is below this 656, then it's an outlier, just remove it. Okay, so this is lowest threshold. Okay, and I can just do df df rain pressure millibar less than this lower threshold, and gives me false and true this, right? So if it is greater than this, then it's still valid data point. Okay, and just pass this to df array. Now I have all the data points where the threshold value is more than this, right? And then I can get the data again. So this is the cleaned column. So what I did, I get all the rows or all the data points where the value is greater than the threshold, then pass it as a boolean parameter for the whole data frame. So I only have the data frames values which are more than the threshold value, right? So basically more than the mean minus 3 standard deviation. Okay, and then get the same column again. So this is the cleared. So it's kind of cleaned pressure. Okay, we'll do a same thing, kind of similar thing on ground, and just pass this clean pressure here. Now see, the distribution looks quite good, right? So the distribution is like this. So mostly it should be around like 1015, right? It's the mean here. So the most frequency is 1015 millibar for this for ring, right? So I can label it as ring. Okay, do a plt.legend to have that legend in the plot here, legend rain. So I know that, okay, rain distribution is this. Let's see what is the distribution for snow. Copy the whole thing, snow, and just replace everything with snow. Sorry. Anything else? df snow. Paste. Snow cleared pressure. Okay, just plot both of them in the same plot. snow air pressure. This will be snow. Color is already managed by the library itself. See, so this is the density for snow. So we see that okay, in case of snow, the air pressure is higher. Okay, wait 1 minute. Okay, so yeah, so what we saw that in case of snow, the air pressure is always higher from when in case of rain. Okay, so we can write the observation. Analysis 3, in case of snow, the air pressure is higher than rain. Okay, so okay, so now see, now we have a good understanding that my data, that whatever data I have in the data frame, right, all the data. So humidity, temperature, I can differentiate by just seeing the graphs. I can differentiate whether it is raining or snowing, right? Okay, from wind speed also I can see, okay, there is a little bit variation, but okay, there is some variation, that okay, in case of snow, the median wind speed is lower, right? So wind direction, from our intuition, it doesn't really make any sense to have any relationship between wind direction and snowfall or raining, right? So we didn't consider them that okay, this cloud cover is already 0, and we can just reconfirm it by just doing a value counts. OUNTS value counts. Okay, see, it's totally 0 of these values, this many values, right? The whole data set is consisting of only 0 values for this column. So you just throw it out. So what are the columns we have that are useful in terms of classifying whether it is raining or snowing, right? Here is the list of columns. List of columns, yeah, here. Right? We'll just now from these plots, what we understand that these features, by looking into the graphs, we can differentiate what is raining and what is snowing. So these can act as a features or predictors. Like these are kind of interchangeably used, predictors or features, these things. Okay. So date format we don't. So summary, this is the actual data summary, whether it is rainy or snowy. This is what? Summary is okay. Summary is partly cloudy. This is label. This is our label. This is precipitation type, something like this. Okay. So we keep the label aside. Label is, sorry, this one. What happened? Yeah, so this is the label. Temperature is useful, fine. Apparent temperature and temperature are correlated, so we only required only one. So if I keep temperature, then I don't have to keep apparent temperature, or vice versa. So if I keep apparent temperature, I don't have to keep temperature. Okay? The humidity, wind speed, fine. This doesn't make any sense to be in the list. Visibility, it makes sense because snow makes visibility lower, right? Cloud cover is 0, so you just remove everything. Okay, pressure, we need that, and daily summary, we don't need that, right? It's particular textual summary of the whole day. Okay, so these are our features, and we already have, these are known as features. Okay, you can just keep them as a list. You can just keep them as list, something like this. Okay, now how to train a model from now on. Okay, so this is up to the analysis part. Okay, now I know which columns impacts rain or which columns impact snow. Okay, now how to model the model model the relation of these features to snow. Okay, so let's go for a very simple model first. Let's go for logistic regression. Okay, so logistic regression, sorry, ION. So what it does, it gives me these kind of thing, this kind of decision boundary. So this is for 2D. So let's say one is X and Y, and the third one is the prediction, this red or blue. Okay, for our case, this X and Y is the features, and this red and blue is the label. Okay, so it gives me a good decision boundary on where the rain would happen, when the snow will happen. Okay, and the inner workings are like very easy, but anyway, not part of this discussion as far as I can say. But let's import seaborn. So import not C1, scikit-learn, SCIKIT, scikit, sorry, sklearn. Anyway, sklearn dot linear models import logistic logistic linear models. So what are the linear models I have? So logistic regression should be here. Anyway, let's just search it. Sklearn logistic regression here. Yeah, linear model logistic, capital L, logistic regression. Import. So, oh, sorry. Here it should be from import logistic regression. Now I have the logistic regression, and so here there are some parameters that you want to tune or not want to tune based on your requirements. So for me, let's keep them as default. Okay, this is my model. So model dot, here I have to do some data processing. So these are known as data post processing. Okay, post processing. And what are them? They are basically splitting your data, or sometimes scaling it or not scaling it based on the requirement. So for logistic regression, there is not a strict requirement of scaling it. Okay, so you can either scale it or not scale it. Anyway, sorry, not post processing, pre processing. Okay, post processing something else. Anyway, so the data is data frame, the whole data frame. From there I am getting the feature columns, all the feature columns, and the label or the target is data frame. I am only getting the label column. Okay, so what it gives me, let's just see, data is actually all the columns of all the features. Okay, and target is rain and snow basically. Okay, now two things we'll do. We'll so actually three things we have to do. First, we have to uh, remove or impute impute the pressure values outside or outlier pressure outliers with mean. Okay, so we put all the pressure outliers. See, here we remove the outliers, right? But there are some outliers which are going to 0, so we just remove all of them. Okay, so remove all of them or impute them with mean. Okay, mean will impute. Okay, anything else we want to do? We want to scale the data, and before scaling it, see, these are exactly the steps you want to do. Okay, before scaling it, you want to split the data. Okay, then scale it. That's the third step. And lastly, you can encode the labels. So basically rain means 0 or and your snow means 1, something like that. Okay, so encode the labels. These are the steps you want to do. So first of all, impute the pressure outlier. So from data, we'll do it separately and put it here. Okay, so data, I have this column with me here, and then similarly here we computed the outlier points. Right, so this is how you compute the lower outlier. So data control V. So this is the threshold, right, for which below it it's all outliers. So you'll get the data where it is below lower threshold. This is a that will give me a true false thing, right? Now if I pass this, it will give me all the pressure values as zeros, right? So here I have to replace it with basically these are all zeros, right? Let me see. If it is 0, there is a better way of representing it. Okay, so better way of imputing it actually. Dot mean or dot value counts. COUN. Yeah. Okay. So we have some 0 values, not other values. So it's not like we have values from 100. These things. These are 0 values. Okay. So what we can do instead is all the 0 values can be imputed from the previous value. So what is the logic? Is that the pressure doesn't drastically change from the last sampled value, right? So what we can do, whenever we have 0 measurement or no measurement, I can impute the data from the past measurement. Okay, so how we do that? Data, this pressure value dot replace or replace here to replace and the value. Okay, so I want to replace all the 0 values with np.nan. So this is not a number, and np I can import it here because it is required. Import numpy as np. So what it does, it imputes all the values from whichever is 0. Now it is imputed as none. I can verify it by doing a value counts. Okay, nan is not there. Okay, replace everything with 0, everything which is nan to 0, and now I do a forward fill, a fill. So what it will do, it will do wherever it gets a nan value, it fills it with the previous value. Okay, and I just do reassignment of the same column again. Yeah, so I assign the currently cleaned column, which is what, replacing 0 values with nan and then replacing nan values with previous values, forward feed. Okay. Okay, I have replaced the whole column. Fine. Now if I do this, I'll say okay, these are the and basically the whole threshold is now like above. I don't have to do a threshold now. So the threshold is now 993. It is a like valid value. No need to do all these things. Okay, just replace them. Okay. So cut this, put it here. Fine. So I have the whole pressure column now cleaned. Now I have to do the splitting of the data. Now before splitting the data, I should encode and scale. Okay. So the steps should be encode should be first. Encode should be first, then split, then scale. Okay. So this should be 2, this should be 3, and this should be 4. So encode levels, so what we will do, we will use a encoder from the scikit-learn library itself, from sklearn dot not ensemble model selection. Let's see where the encoder is there. Sklearn label encoder. It's in pre-processing label encoder. Okay, so from sklearn pre-processing input label encoder. So what we will do, label encoder is equal to label encoder dot fit transform target, and you have the target, reassign of target. Okay, so what it does, let's see. Target, what is target now? Target is 0 and 1s, right? Now what is the encoding we got? I can see that label encoder dot classes, it will give me okay, rainy, snow and nan. So nan is also there. Okay, if nan is also there, why nan is also there? Df should not have nan, right? But there are some nans. Okay, anyway, so what we can do, we can just do df is equal to df dot drop now. All the nan values are dropped at the beginning. Now we don't have this type of things. Okay, now we have only snow and rain. Okay, and the targets, so snow, rain means 0, snow means 1. And if I want to see that too, transform, okay, get params. Okay, no parameters, only classes. This classes is gives me the index is the encoding. So rain is 0, snow is 1. Okay, anyway, the target is now set, label encoder is okay. So now pressure column is also fine. Now splitting the data. So how we can split the data? X, so it is from sklearn dot model selection import train test split this. Okay, and to see what train test split gives you, if you give you, so it gives you splits among training testing sets. Okay, so what it expects, you can see in the example here this, that you give you if you give it x and y, it gives you x test x train x test, y train y test, right? And the test size is 0.33, which it will keep 30% as the testing sample. Okay, so just copy paste this line here. For x we have data, and for y we have label, right? Or target. So now I have the sets. These are not scaled yet, so I keep 33% as the testing set, and these are not scaled. So how we will be scaling the data? Let's just run it once, see what x train is. Yeah, extrain is this unscaled value. Okay, and these are randomly split. So these data points are actually randomly taken from the whole data set. Okay, 70% randomly taken samples. Okay, now from here I can, from sklearn dot pre-processing, import what, import scalar, right? Let's just do min max scalar. You know, already know what min max scalar is, right? X minus x min divided by x max minus x min, that is the min max scalar. So I can just import it, apply it here. Mean a scalar is equal to min max scalar, and see, this is something you should like just know that we should apply the scaling on, or we should learn the parameter for scaling from the train set and just apply it on the test set. Okay, so because why it is so is because we know the train set, right? We don't know the test set beforehand. That's our assumption, that the test set is not seen by us as well as the model. Okay, it is something very unknown. So we don't know what is the minimum and maximum value for test set, right? So in that case we will only learn parameters like minimum maximum value for all the features from the test set itself and not the train set. Okay, so to do so, the code is like this: scalar dot fit. Okay, and I will only fit on the xtrain data. Xtrain is the features from the train set. Okay, y train is the labels from the train set, and then just transform the xtrain data from the xtrain data is equal to scalar dot transform xtrain. So I will learn the parameters from min max, all the parameters from xtrain, and then transform the xtrain. So what it will do, it will apply the transformation and make all the columns vary from 0 to 1. Okay, same thing I will copy. See, I have learned the parameters from train set. Okay, but I am applying the same transform in the test set as well, because I don't know the minimum maximum value of test set. So in that case, sometimes let's say when the test set has some larger value than the train set, it might happen that the feature is crossing 1. But okay, anyway, that is none of our concern. Okay, so that means the test set has some values which are higher than test set. So there can be always this type of instances. Okay, and to combine these two lines, right, we can directly do fit transform. Okay, fit underscore transform. So what it will do, it will fit the data on this data, fit the mean max, all the parameters from this data, and then transform it. So it will return the x test. So this is the kind of optimized code. Instead of fitting and then transforming, I can fit transform on x and just transform on test data. Okay, so now scaling is also done. So 4 steps. See, impute any value which is outlier. Okay, drop any value which is not there. Now encode the labels and then split the data, scale the data. Fine, now run it. Run. So I have what, xtrain is what, xtrain is a matrix of all the scaled values. Okay, that is y train. Y train should be a list of all the labels, Okay, similarly x test and y test. Now what I will do, I will run the model. So this is a logistic regression model. What it will give me, it will give me this type of a decision boundary from all the, and see, so for this example it is 2-dimensional thing, right? So these are only 2 features, x and y, and the decision it is making is red or blue. Okay, so that label is red or blue, or the target is red or blue. But for us it is how much dimension? It is, what are the number of features? So 1 2 3 4 5. So it's a 5-dimensional or 6-dimensional plane, or rather 5-dimensional plane where the color is basically rain or snow. Okay, so similarly you can assume a 6-dimensional or 5-dimensional plane where there are 5 axes representing wind speed, wind direction, or not wind direction, wind speed, temperature, humidity, all those things, and the color of the dots are basically rain and snow. Okay, and our model is doing what? Our modeling is generating this separation, this green line between whether it is snow or a rain. Okay, just say, and it's very similar. So whatever we are doing for this fit and transform, this is similar. So we will fit the data, fit the model from the data of the X train and Y train. So this is how you fit the model. Okay, run. Okay, it is currently trained on that data. Okay, the logistic regression model is trained on the training data, and if I want to test it on the training data itself, I can do this. Predict is equal to model dot predict on X train. So what it will give me? It will give me the classes of prediction. Okay, this is what the model thinks from the data. It thinks whether it was raining or snowing, and I have the true data for it as well in Y train. So I can now compare, see how much accuracy it has on the training data. So how you can compare? I have all the metrics that I can import from here, from sklearn dot pre-processing import. So what things I can import? I can import confusion matrix. So not pre-processing metrics. Okay. Matrix import confusion matrix. Let's say accuracy score, and let's say classification report. Or actually classification report will give me everything. So just print classification report for now. Okay, not the confusion matrix. So prediction and Y train I have. I can just do classification report, and it gives Y2 and Y predict. So Y train is the first parameter and prediction is the second parameter. This is the so this, it gives us a string, right? So I have to print it actually to have it printed here. So there is a formatted string actually. See, so the overall accuracy is 99% in train set. So for training, I can clearly say for 99% of time whether it will be raining or snowing. Okay, and for each class, so each class for 0 is for rain, 1 is for snow. So for raining I can say 99%, and for 1 whether it is snowing I can say it and as 95%, right? But these are for training set, right? So it's obvious that the model is trained on the training set, so it's obvious to perform well. But for test set, wherever the data is unseen, let's see how much it can predict on the test set. This is the test set. This is test prediction. Yeah, just do replace these things with Y train, no, Y test, right? Print it. Now see, I can also print, I can also predict whether it will be training, whether it will be raining or snowing with similar accuracy for the test state as well. Right? So what we learn from this, that okay, so the whole learning for this one is okay, I from the data set I can analyze each column and understand how they can help us differentiating the target class, right? So we know that okay, temperature, we have this observation that okay, for if rain happens the temperature is high and humidity is relatively low, but whenever the snow is happening the temperature is very low and the relative humidity is also high, right? Similarly, we observe that okay, this indoor temperature and temperature are correlated, so we should keep only one column. We should not keep correlated columns because it doesn't give us. So why not we keep two correlated columns? So for example, see, this temperature and apparent temperature actually related equivalently, right? So y is equal to x, this relationship we have, right? That's why if I give one parameter, it inherently gives the information for the second parameter. We don't have to give it separately. Okay. So by doing this, what we are doing, we are reducing the computation for the model as well as like reducing the total data required to train a model. So there are some, so So there is a cool relationship that whenever the number of columns increase, you should have more data points as rows to be learned, okay, or to learn the data. So because we are basically removing the correlated columns, so what we are doing, we are actually increasing our learning capacity, that we can learn more from this data, right, because we are reducing the width or the number of columns that we are passing. Okay, so one key observation here, we should not include correlated columns of any data together in a modeling. Okay, we should only keep one column that represents all the correlated columns. Okay. Okay, similarly for wind speed and visibility, these are very, so what we observe that wind speed is not that much correlated or that much uh, like kind of indicating snowing or raining weather, but wind visibility is really decisive factor, right? So for snow the visibility is really low. Okay, similarly for pressure, we observe that for rain the wind the atmospheric pressure should be lower than the snowy weather. Okay, so yeah, after all these observations, what we found, these are the analytics part. Okay, this is the analytics part that you do, and what you found, okay, these are the features that are most promising for my learning task. That okay, I want to predict whether it will be raining or snowing, right? So the most promising candidates from my whole data set is these things. Okay, and then we go with these are standard things, so you can apply imputation, label encoding, split data and scaling data in any learning task. So it's very standard, pretty standard approach. Okay, so you impute the data, all the missing values you impute with mean or any other thing, you you encode the label in integer values, because the models works in terms of integers, or let's say floating point values, right? So they don't take floating point in, they don't take text as targets, right? So you have to encode them in terms of 0 and 1. So for us, rain is 0 and snow is 1, but we encode it, right? And then you have this splitting and then scaling. One thing you should remember, that we should only learn the minimum maximum values and all those parameters whichever is required for scaling. For example, for a standard scaler, the parameters are mean and standard deviation, right? So to have those parameters learned, we just use the training set. We don't learn parameters from the test set, but only apply the transformation on the test set. And because we know that okay, test is something that we don't know, so we should not use that for learning or scaling anything with the test set. Okay, similarly, like this model training and everything is pretty standard. So you just do any model name, you give it here, fit, and then test. So these codes is pretty much same for all the models, whichever is there in sklearn. If you want to change some parameters for the logistic regression models, these parameters you can tune from here. But anyway, you have to know how this model work before you can tune them. Okay, anyway, so yeah, any other model you want to try is just changing the model from here. Instead of linear model, let's say I want to do a disease entry model, right? So just replace the model with disease entry, it will give me the corresponding these scores, right? The prediction accuracy and all. Okay, so now this is kind of a whole analytics and modeling pipeline you do. Okay, some examples I can show you. For example, wait, for example, let's go to my data set. Okay, so this data set.
I have a very general question.
Yeah.
Suppose we are given a data set, or we have a data set. So like before starting this analysis, we should be having a question in mind, like what is our target? Only
Yeah,
then we can go to that
yeah,
direction.
exactly. So it is like, so I have an idea what I want to solve, right? By seeing the dataset documentation, right? I have an overall idea that what I want to solve, or what I
No,
want to.
so this documentation will be available only for data which are available
Yeah,
on like on Kaggle or some such platform.
yeah,
But
GitHub,
suppose
let's say.
it's a very raw data on some government website or something, like some healthcare data on a government website, then we are downloading it. Then looking at the data, we should create the question like what can
Yeah,
be done from it, or we should be having a question in mind,
yeah. So it
and
is
then
like,
select a data set.
yeah, it's like, let's say I want to know how my health parameters impact my chances of getting COVID, right? Okay, so these type of
Mhm.
problems I have to, so it is not like I am going getting some random data set and doing analysis on that. It should be like I have a problem formulation in my mind. Okay, okay, this is, I
Okay.
want to see what, how they are related first. Okay, and
Okay.
then I go and search for related data sets. Okay, now I have this target which I am supposed to like cover, or let's say explore, and all the parameters associated with that data or that column, let's say COVID, right? All the parameters,
Mhm.
say blood pressure, sugar, all those readings I have it from, let's say, any medical site, or let's say government site. I download the data and then I start analyzing. Okay, so basically the pivot thing, or whichever I am doing analysis, that should be first put to the center, that okay, I want to analyze healthcare data to understand how likely I am to get COVID in different health situations, right? Then my analysis starts, and I cure the data from different sites.
Okay.
Okay, so it should be something like the problem formulation should be first step established, then we go for data collection, analyzing, because then your problem formulation will help you figure out the questions, right? Which questions you should ask
Yeah.
for analyzing the data. Yeah, that's the general approach.
And then the data set we get, like I'm not sure this data set. So like how, so first step should be like checking if the data is normalized or not.
No,
uh,
no, 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 no. So this should be this would not be normalized, right? Because if they are already normalized, then you don't know the high value, the low value, these things. They should not be normalized. So they should be raw, and then you analyze the raw data before going for modeling. You normalize the data, because for modeling part the normalization helps. But if I, let's say, give you heart rate values in 0 to 1, then it doesn't make sense to us, right? It should be from 90 to, let's say, 170, something in this range, right?
yeah, if it's not normalized between 0 to 1, but if it's like if it's a state wise data and it's giving me
Uh-huh.
averages, so averages of all the people in a state. So
Mm-hmm.
like for MP this much, for UP this much, for Rajasthan this much, that way.
Uh-huh.
Then it's already giving me averages of the condition
Yeah,
in that state.
yeah, yeah.
So
And they should be
then
also reporting standard deviation, right?
standard deviation between the states.
Yeah, yeah, within the state. So the mean is this and the variance is this, let's say.
No, no. So it doesn't give the standard
Variance.
deviation. It's just giving the means, like in a
Okay.
table. So
Okay.
then,
So
do we consider it as normalized or?
no, 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 that is not normalized. That is actually average data you are getting, right? So
Okay,
normalized means it is normalized from 0 to 1. So normalized in a
okay.
range. But
So then we
these
can normalize it before modeling,
yeah,
like,
before modeling you can just normalize it. Yeah, before
okay.
modeling you
And
just get
then
the max anything.
using
And
using this, we can do a comparative analysis between
yeah,
the states.
yeah, without the scaling part, or without the normalization part, you compare between the states with the raw data, and then before, like, understand which columns are useful for your analysis, and then go for a modeling. Take only those columns that gives you a good understanding of the target. For us, let's say these things, right? Temperature,
Okay.
humidity, all those things. Yeah.
Uh, okay.
Okay.
Thank you.
Okay. So I hope this is good. So anyway, so I'll upload the whole code in the drive. and the presentation as well. Okay guys, so see you in the next week then. I'm stopping the recording.